Great, thank you. Thank you for the invitation, and happy to be here today. Um, I would just like to acknowledge three people who have contributed both data and some interpretations to what I'm going to present. Chris Connors is a structural geologist and seismic interpreter at the Washington and Lee University in Virginia. Bernie Coakley at University of Alaska Fairbanks collected a seismic grid that has been important in the work that we've done. And Tabia Altenburnt from Alfred Wegener Institute has spent a couple of intervals of time here in Virginia with me interpreting the seismic data that we're going to be looking at today. Let's see. There we go. So Carmen's presentation set me up beautifully because she explained the broad origin of the Ameracia Basin, of which the Canada Basin is the southern part. She also showed the Chukchi borderland, which is a prominent feature in this study. And the southern part of the Alpha Mendeleev Ridge lies here in the Chukchi Abyssal Plain. The North Chukchi Basin, which I am going to speak about, lies in the U.S. Chukchi Shelf, the northeast Russia Siberian Shelf, and in international waters beyond the EEZ, which is shown with this dashed black line. I'll also point out the Wrangell Herald Arch, which is a key component of especially the Cretaceous history of this region, as is the Western Brooks Range. The fold thrust belt that comprises the Wrangell Herald Arch and the Brooks Range origin commonly are linked genetically, and in fact they overlap a great deal in time, but from my perspective they are different beasts. The Brooks Range origin is mainly a collision between a continental fragment that underlies the north slope of Alaska and a magmatic arc system to the south, related to the closing of the Angeuchum Ocean Basin, whereas the Wrangell Herald Arch was more related to continent-continent collision when the South Anui Ocean Basin closed during the late Cretaceous and late Jurassic and early Cretaceous. So this area is quite interesting from a sedimentological perspective. I am a sedimentologist, so that's the way I approach life. And if we look at the stratigraphy of the area, this is a stratigraphy based on the rocks that have been penetrated by exploration drilling on the Chukchi Shelf. What we see is a section that includes rocks as old as Devonian and as young as modern. However, when we move into the North Chukchi Basin, what you will see is that we are limited to rocks of probably Jurassic and younger. The Jurassic section is influenced or was influenced by the actual rift opening of the North Chukchi Basin, or at least the upwelling related to the early phase of rift opening. So the Jurassic unconformity is an important constraint to interpreting the North Chukchi Basin. And as we move up section, we have two main phases of sedimentation. One that is Cretaceous in age, and the other which is Cenozoic in age. And this basin fill, comprising these two main depositional systems, was derived mainly from erosion from the Western Brooks Range origin and the Chukotka origin, respectively. Significantly, there is deformation that creates this middle Brookian unconformity between the Cretaceous and the Cenozoic, and that's related to a foreland fold thrust belt system that deforms the eastern end of the Chukchi Basin, North Chukchi Basin, as you'll see as we go along. The data with which we work here is based on both well data, a lot of seismic data, and gravity and mag data. There are 6 exploration wells that have been drilled on the U.S. Chukchi Shelf. I only show 5 because I haven't updated the drafting on this figure for a few years. The 6th well was drilled as a twin to the well just here, and the disappointing results from that well resulted in Shell Oil Company departing certainly the North American Arctic, if not the entire Arctic. The magnetic data shows the North Chukchi Basin very clearly, and I'll point out the very high amplitude signature of the alpha LIP, large igneous province lying to the west of the Chukchi borderland, and also the bit of high amplitude or high magnetic anomalies that Carmen referred to along the eastern margin of the Chukchi borderland. This would be the high-standing North Wind Ridge that she referred to. Also, the gravity is very interesting. The gravity signature on the north side of the basin varies, or the gravity signature varies quite significantly from east to west. This I will get into when we look at the seismic data, but the main deep part of the North Chukchi Basin is well defined by the significant gravity low. Things over in the Russian Siberian, East Siberian Shelf get a little bit more complicated, and the interpretation of that mainly refers back to the East Siberian rift system that underlies the deep part of this basin. The seismic data is very dense on the US side of the Chukchi Shelf, as you can see here, less dense on the Siberian Shelf of Russia. These are the seismic grids that we have worked with. Bernie Coakley's grid is the one shown here in green. And actually, I haven't updated this figure either because I've also licensed now a seismic grid that fills in some of the gaps here between the very dense 2D seismic coverage on the U.S. Chukchi Shelf and the southern border of the Chukchi borderland up here to the north. So if we look at the sediment fill of the North Chukchi Basin, it is enormous. Let's see, I need to try to move. Oh, there we go. Oh, there we go. So we have a sedimentary section that is up to 11 seconds and closer to 12 seconds in thickness in some areas. And using the Art Grant's depth time conversion that was generated for the North Chukchi Basin, the Chukchi Shelf, and the Beaufort Shelf, we must project pretty significantly and estimate that the maximum sediment thickness here is about 20 kilometers. And I'll show you some seismic data that actually allows us to talk about the character of that basin. This basin is interesting because this is just the seismic data shown again. And again, there are the 6 exploration wells on which we base our age correlations across this basin. I talked about the fold thrust belt in the northern part of the Chukchi Shelf. This is the area that is influenced by deformation. And what we see is that this basin opened, and I'll show you the evidence for that as we go along, and was sediment starved for a significant amount of time. The early sedimentation in this basin is Cretaceous in age, and it was derived mainly from the Brooks Range and filled the eastern part of the basin with a very thick sediment section that is absent or very minimal as we go westward within the basin. The deformation that occurred here spans the Cretaceous Cenozoic boundary, and that, as I'll show you in a minute, is a doubly vergent fold thrust belt with both south vergent and north vergent thrusting, and then that is complicated subsequently by strike slip and normal faulting that opened a rift system during the early Cenozoic beneath the Chukchi Shelf of the US. So just to show you two seismic lines showing you the nature of the fold thrust belt that lies well north of either the Brooks Range fold thrust belt or the Chukotka fold thrust belt. This line I've shown here is the southern segment of the line, and you can see south vergent thrusting with back thrusting forming a passive roof duplex. And so what we see here is most of the sedimentary section that ranges from late Devonian through early Cretaceous in age was actually truncated over this southern segment of the fold thrust belt. And again, the age of that thrusting ranges from very late Cretaceous into the early Paleogene. The northern segment of this fold thrust belt with the north vergent thrusting is shown here on the north side of what's called the North Chukchi High. And you can see here the north vergent thrusts very clearly with growth strata above the fold thrust belts and the fault bent folds that formed. And that is what we use to date this deformation as latest Cretaceous and early Paleogene throughout this area. So that is the character of the deformation that I referred to earlier as the North Chukchi deformed domain, and that will become important as we start to look at some of the seismic data. So this long line shown here is west of the Russia-US maritime boundary. It is a little bit east of Wrangell Island, which is shown there, and this crosses the entire North Chukchi Basin. So this is the Wrangell Herald thrust belt on the southern part of the line. You can see the deformation. This seismic line traverses the basin for about 450 kilometers. And on the north end, this sedimentary section is actually downlapping onto the Chukchi abyssal plain just south of the LIP that I talked about earlier. The base of the Brookian section, so this is mainly Cretaceous and younger section, lies approximately on either oceanic crust or exhumed mantle, and I'll elaborate on that interpretation as we go along. And it is a section that is mostly Cretaceous below this pink line and mainly Cenozoic above that red line. The MEU is a Middle Eocene unconformity that is widely traceable across the region. And I'm also showing the top of the Oligocene here in green as a marker. We have mapped all of the shelf margin rollovers and the trajectories of the shelf margins. I won't say very much about that today. I'll concentrate more on the origin of the basin as a whole. One of Bernie Coakley's lines is very critical to the understanding the geology of this area. It is this short segment shown here on the map, and it is shown there. And what we can do is jump correlate a short distance between these two lines to build a seismic image of the complete North Chukchi Basin from the Wrangell Herald Arts Fold thrust belt on the south to the high-standing continental crust of the Chukchi borderland on the north. And again, the stratigraphy is the same as shown above. You will notice, though, that there is a little bit more charm here on the north flank of the basin, and I have labeled that charm SDR, seaward dipping reflectors, and I'll show you close-ups of that in just a minute. The real interesting part of this basin is that we appear to lack continental crust across most of the width of the basin. And these wavy dashed lines on the north and the south imply an approximate moho section and the interpretation of exhumed mantle forming as this rift basin opened is very appealing but difficult to prove with the limited data that we have available. I will point out that Sergei Drachov in 2018 interpreted what underlies this basin as thin lower continental crust or exhumed mantle. Earlier interpretations by Granath et al. Have mainly focused on oceanic crust or exhumed mantle, so there's still some debate in play about exactly what lies beneath this 20-kilometer section. And again, pointing out the depth here, the base of the Brookian section here, and this particular line is between 10 and 11 seconds. So we're down approaching 20 kilometers of sediment thickness at this point in the basin. Just to show you the SDRs, one of Bernie Coakley's postdoc students published this a few years ago in Marine and Petroleum Geology. It shows the character of what we have interpreted as seaward dipping reflectors at the very southwestern corner of the Chukchi borderland. And the Russians, one of Nikishin's students, Rodina et al., presented this also a couple of years ago, or just a year ago, actually, showing the seaward dipping reflectors along the western margin of the Chukchi cap or the Chukchi platform. So as shown earlier by the magnetic anomalies that are associated with the LIP in the basin to the west of the Chukchi borderland, we do have volcanic influence indicated along the southwestern and western margin of the Chukchi borderland. Just a little bit more background on this and a tentative interpretation. The paper, the recent paper that really serves as a bit of an analog in this area is the paper that was published by Jim, what's his name, and where's the reference cited here? It'll come up next. I forget his name off the top of my head. But what we have on the southern side of the basin perhaps is a magma pore margin where we don't see any evidence of seaward dipping reflectors. In contrast, on the northern flank of the basin, we do have seaward dipping reflectors that are more indicative of a magma-rich margin. So there are analogs for both areas that were published in this Jim Pindell paper, and this works, or this is being used by us as a working model for the evolution of this rift basin as it opened between the continental crust on the south along the Chukchi margin and the Chukchi abyssal plain on the north. A little bit about the west to east relationships we see in this basin. Again, this is the line that I showed earlier on across the basin from south to north. If we look at the line longitudinally in the basin, we can see the influence of that North Chukchi deformed domain that I referred to. So the deformed section below this pink horizon that's labeled MBU is characterized by the kind of doubly vergent thrust faulting that I showed in the two seismic images previously, subsequently broken up by normal faulting during the Cenozoic. So you can see a great deal of relief actually from south or from west to east on this deformed domain. And in fact, it's about 4 seconds of relief, which results in an approximate depth of 8 to 10 kilometers. So we're really looking at a fold thrust belt in the eastern end of this basin with 10 kilometers of relief. And the sedimentary section on the Russian side of the border contains between 8 and 10 kilometers of section that is essentially missing on the U.S. eastern side of the border. Just carrying that longitudinal section a little bit farther into the really heart of the deformed zone in the east, I've just taken this longitudinal section that I showed in the previous slide, moved it to the west a little bit, and I've added some shallower seismic data across the more deformed part of that fold thrust belt. And so you can really see the relationship that exists between the very, very thick section on the Russian side of the North Chukchi Basin and the section that was deformed at the Cretaceous tertiary boundary in the eastern part of the section. The other thing we can do with the data sets that we have available is build a north-south seismic section across the U.S. side of the border. And there is a 40-kilometer gap between these two segments from south to north. But what we can see here is a very narrow part of the North Chukchi Basin where it lies above the fold thrust belt. But we still see what appears to be either the emergence of exhumed mantle in the deepest part of the basin, or an incipient situation where the basin simply did not open as far as it did farther west. So if we kind of put those two together, the long north-south line in the west and the shorter segments in the east, what we can see is a complete cross-section in the west from the Chukchi foreland into the Chukchi borderland, and farther to the east then in the east end of the system, a more narrow system that looks like so. I've used another Jim Pindell figure to sort of imply that this is analogous to 2 stages of opening, a progressive opening of a rift basin. This particular model was drawn in the Gulf of Mexico, but nevertheless, it can be used as an illustration of a rising continental or subcontinental mantle in the eastern part of the North Chukchi Basin, and in the west, a fully open basin that has emplaced subcontinental mantle, or perhaps even oceanic crust forming, although we don't see direct evidence of that in the North Chukchi Basin. So to just conclude, we have a rift basin with up to 20 kilometers of strata, thin to absent in the pre-Brookian, mainly a lower Cretaceous through recent Brookian sedimentary section. Sediment was derived from both the Chukotka and Brooks Range origins. We infer that rift opening occurred probably between the mid-Jurassic and the very early Cretaceous, and very much analogous to the Canada Basin just to the east, and that the basin is floored by exhumed mantle or oceanic crust. And with that, I'll say thanks for listening, and I'll be happy to answer questions if I can.
Thank you so much, Dave. That was a wonderful overview and beautiful data. There are no questions in the chat, but the co-conveners are fighting to ask you a question. I'll give Fola the floor first. Fola, do you want to ask your question?
Sure. Thanks, Dave. Really nice talk and really fascinating work. So my quick question is, it's pretty interesting to see overlaps, spatial overlaps between, contractional structures and extensional ones. Now, I'm wondering if you've seen any evidence for inheritance, of the older contractional structures in the development of the rift.
Not only that, but the inheritance goes all the way back to actually pre-Devonian. Chris Connors and I have a paper in press right now in marine and petroleum geology that traces the inheritance in the area of the Chukchi, of the Hannah Trough. And let me just go backwards, if I can get this thing to go backwards. I'm going to go back to the beginning so I can show you a map. Lying beneath the Chukchi Shelf is the Hannah Trough, and papers that have been published by people like Naresh Kumar and others have shown that the Hannah Trough essentially is a suture. And it is a suture between Laurentia and segments of the outlying continental blocks that collided with Laurentia during the Devonian. And so underneath the Hannah Trough are Devonian aged fold thrust belt that represents the closing of that suture. That was followed in the Mississippian and Pennsylvanian by extensional east to west extension in the Hannah Trough. And those extensional faults very much sold into the Devonian thrust faults. We go up to the Jurassic triad. There is a cross-cutting set of extensional faults that have been documented recently by Tom Hamza and Steve Bergman in an AAPG memoir. Those also have inherited fabrics from the earlier structures. And right now we're working on the deformation up here at the Cretaceous Tertiary boundary, and it's very clear that there are many cases of the fabrics of the earlier structures influencing and controlling the geometries of the younger structures. So we have at least 4 stages and maybe 5 stages of structural inheritance. That's one of the reasons that the seismic data on the Chukchi Shelf are very difficult to interpret.
Thank you.
And Gianrotto, do you have one last question before we wrap up?
Yeah, I was wondering about your interpretation of the base sediments.
Yes.
You have these 20 kilometers, and there is this 10-second rules that you might know. A guy called Warner, he actually said that if you are in isostatic equilibrium, if you have no flexion, no dynamic topography, MOHO should be at 10 seconds. And that makes that in rifted margins, if you go down at 10 seconds with sediments, you have exhumed mantle. You should have exhumed mantle, but you go even down below 10 seconds. And so at one point I was asking me if your base Brooklyn is actually not MOHO, and that actually the top basement is a bit shallower. So that was because it's very this is not, it's the strike line, because if you go on the strike line, if you go there was another strike line.
You mean the west-east line? This one?
Yeah, exactly. Yeah, because this one, because you see that you have a very strong reflection at the base, you have about almost 2 seconds, and then you have a flat top. So I was asking me if this could not be normal oceanic rust. And so if the red line is actually really the base of the sediments, or so that was a little bit my concern, because on one hand you show that you have SDRs on the mountain, so magma rich.
Yes.
And suddenly the basin should be magma poor. And so that was the same in the last presentation. So I'm wondering if the interpretation of the margins and of the deep interpretations is actually, it's okay.
Yeah. I need one of my co-authors to help me out with this question, but they're not here today. So that's an excellent point, and it's a point that needs to be addressed. And I'm not sure that I have an answer for you, but what we believe based on the correlations is that as we move from the east to the west, some of the reflections that we are interpreting are probably condensed section source rock sections, petroleum source rock sections, because they correlate with source rocks both in the Cretaceous and the PETM source rocks. And below the Brookian, we're fairly confident of this base Brookian because of that very extensive seismic data set we have tied to wells on the U.S. Chukchi Shelf. But certainly, you raise a good point. And, with so little data out here, we need to take all suggestions like you've made into consideration. And so I'd very much like you to send me an email and let's correspond about that.